Good afternoon. Um, Again, we're going to be continuing on with polynomial functions, and there was quite a bit to look into the other day. A lot of the mechanics involved, a lot of the micromanaging details, and in a sense, you have a continuation of this. And we looked at last time the end behavior of the graph of a function along with zeros and their multiplicities. And again, we have just going back to end behavior. Okay, say if you have a polynomial function and you have the highest degree term, okay, to have a leading coefficient that is positive while the degree of the polynomial function is odd, you're going to have the end behavior to be down to the left and up to the right. And if you have a positive leading coefficient and the degree of the function is even, the end behavior, you'll have the same vertically at both ends, where you have up to the left and up to the right. And for the cases where the leading coefficient is negative, okay, we have, while the degree of the function is odd, you have the end behavior to be up to the left and down to the right. And we have in the fourth possible case, okay, whenever you have the leading coefficient to be negative while the degree of the function is even, the end behavior, okay, you have down to the left and down to the right. Okay, so we've had zeros and multiplicities, end behaviors, and also in approximating, okay, what the degree of the function could be. Okay, we have yet another added detail, and this will be what we have in the case of what are regarded as turning points. And this is going to be reminiscent of what we had whenever we were looking at relative minima and maxima. And for what we have regarding turning points, okay, we have the number of turning points. And this will be your combined total of relative minima and maxima, but just some details of what we have regarding the number of turning points with respect to the degree. We have the number of turning points of a polynomial function, and we just call this f of x. Will be at most, and I'm going to stress the at most part here. Okay, we'll have at most, will be at most, okay, one less than the degree of the function itself. And another way that you could phrase this is that the degree of f of x will be greater than the number of turning points and the degree is going to be greater than the number of turning points by an odd value that is at least 1. And let me say, instead of odd value, let's say an odd difference that is at least 1. and just give you a bit of a visual. Okay, if I were to have a graph, and say if I were to determine 3 key components. Okay, say if I'm looking at determining, okay, the sign value of the leading coefficient, the number of turning points, and the possible degrees in of f of x. Okay. Okay, so I'm just going to insert a graph. Okay, just do a bit of a rough sketch here. And we'll say that we have with this function. Okay, so I didn't mean to erase the whole thing. Okay, so for what we have in this particular case, now for the end behavior, okay, you're looking at the extreme left and the extreme right. Okay, so you got down to the left, and we have to the far right. Okay, we have upward motion. Okay, so just using as our building blocks. Okay, so we have for the end behavior, okay, so you have down to the left, up to the right. Whereas Alex might say falls to the left, rises to the right. Okay, now we've got the end behavior. Okay, so what are the characteristics of a function that has this type of end behavior? So you have down to the left, up to the right. So you will have a positive leading coefficient, and the degree itself is going to be odd. Okay, so n is going to be some odd power. Okay, so we got for the first part. Okay, we have that the sign value of the highest degree term coefficient is going to be positive. And now, in the case of what we have with the number of turning points, okay, so you're just counting up the total of the combined minima and maxima. Okay, so reading from left to right, so you have first, okay, have relative maximum followed by a minimum, and you have alternating between relative, minima, and maxima. Okay, and so in this particular case, All right, so you have a combined total of 6 minimum, relative minimum, and maximum. Okay, so you're going to have 6 turning points. Okay, and in terms of what the value of n could end up being, okay, so n is an odd value. And remember, the degree of f of x, which is going to be n, will be greater than the number of turning points by an odd difference that is at least 1. So n is going to be greater than 6, and n is going to be an odd value. So in this case, right, n cannot be 1 or 3 or 5, because that each of them will be less than the number of turning points. So you want the odd value to be greater than 6. So n could be 7, it could be 9, it could be 11. If it's not any of those three, it'll be some higher odd number. Okay, and now let's say that if we have another situation that's also going to consist of turning points. And let's say we have here all right, so you have for the end behavior, again, you have at the extremes. Okay, so you have down to the left and down to the right. All right, whenever you have the same vertical motion at both ends, you're going to have an even powered function. And again, just like in the case of a quadratic function that has negative leading coefficient, we have the graph to be opening downward. We're going to be going down to the left, down to the right. So your leading coefficient is going to be negative, so this will be the last of the 4 cases, and once again the degree will be even. And concerning the turning points, okay, so we have 1, 2, 3, 4, 5, 6, and 7. Okay, so this one we have 7 turning points. And for the possible values n, okay, again, the degree is going to be greater than the number of turning points. N is an even value, so among the possible values could be 8 or 10 or 12 or some other higher even number. All right, and we'll combine those concepts along with what we have had with the zeros and their multiplicities. And for what we have in reference, okay, to the set of problems from page 266. Okay, and we have for the case in number 48, and we have the graph is laid out, okay, whereupon we're going to have three x-intercepts. Okay, and so we have so you have -4 as well as -1. Also have x equal to 3, and with the nature of the behavior of the graph. Okay, so we have so you have at -4. Okay, the graph is going to cross, and once we get to x equals -1, okay, the graph is going to cross again. And then we have, once we get to x is equal to 3, okay, now the graph is merely going to touch the x-axis. And just some of the details that we have here. So the end behavior, okay, we have vertically up at both ends. Okay, so you have up to the left and up to the right. So for what we're going to have in this particular case, all right, so we have the same vertical motion at both ends. So n is going to be even, and since the motion is upward, okay, we're going to have that the leading coefficient is positive. And we'll have that n is going to be an even value. And looking at also the number of turning points, okay, so you've got 1, 2, 3. Okay, so you got 3 turning points. Okay, so looking at what we have here, okay, now this problem in the case of, this problem again was number 48, and looking for the minimum degree that n could be. Okay, so n is even, there are 3 turning points. And for n, okay, so we're looking at just the minimum value n. So the minimum degree n, okay, that is going to be at 4. Okay, and this will be for what we have in the case part A. And part B, okay, was like a little bit of chicken or the egg situation. And part B was asking for the sign value of the leading coefficient, and that is going to be positive. And now, for what we have in the case of part C, okay, we're looking at determining whether the multiplicities of the zeros will be odd or even. And again, so we have with the zeros. Okay, all right, so you have x equal to -4, we have x equal to -1, and we have that x is equal to 3. And in terms of whether the graph, I'm just going to use a little bit of shorthand, like in terms of crossing or touching the x-axis. And so we have in this particular case, right, so at -4, okay, the graph is going to cross. -1, it also crosses. And at 3, okay, it's going to touch. And whether the zeros will have odd or even multiplicity. Okay, so if we had the graph to cross the x-axis, then that 0 is going to have odd multiplicity. So we have odd multiplicity for -4 as well as -1. And in case of where the graph touches the x-axis, it'll be that 0 is going to have even multiplicity. Okay. And now, just sort of doing a bit of shifting of gears. Okay, now we have in terms of a specified function. Now we have, in the case of number 59, okay, we have a given function f of x. Okay, that is equal to x cubed minus 5x squared. Right. And looking at the details on this, okay, so again, the higher or the highest degree term, okay, that is going to be x cubed. And looking at what we have for the details, okay, now we're going to have for the leading coefficient, again, for x cubed, you can read this as if it were 1x cubed. Okay, so leading coefficient, okay, is 1, so this is going to be positive. And with 3, okay, we're going to have that the degree is equal to 3. Okay, so we have an odd value, and we have, with again a positive leading coefficient and an odd power, again this is going to summon, okay, the first case. All right, so you have positive, odd in the leading coefficient and degree respectively. So the end behavior, we're going to have down to the left and up to the right. Okay, so this will be what we have in terms of the extreme ends. Okay, now in terms of the in-between elements, namely the zeros. So going back to this third order binomial, okay, if I'm looking for the zeros, so we have for x cubed minus 5x squared, okay, we have the greatest common factor is going to be x squared, and we have times the quantity of x minus 5. I'll just copy this, okay, just to stress the degrees. Okay, so you got x to the second. And for x minus 5, okay, that is going to be to the first. Okay, and looking at identifying the zeros. Okay, so from the x factor, we have x equal to 0. And for the x minus 5 factor, we have that x is equal to 5. Okay. And in terms of the multiplicity, okay, so 0 stems from x, which is taken to the second power. Okay, so 0 has a multiplicity of 2, whereas for 5, this stems from x minus 5, which is our first order. And in terms of crossing or touching the x-axis, okay, so anything that has an even multiplicity, 2 being such a case, all right, you're going to have the graph to touch the x-axis at that 0. So it's going to touch at x is equal to 0. And anything with an odd value multiplicity, it'll be at that 0 that the graph is going to cross. And there's one other detail, and I know that Alex has been known to ask for this, and that is going to be in the case of the y-intercept. And for the y-intercept, okay, you're looking at solving for y, as x is set to 0, so you have for y. You have f of 0, and it turns out that both of these variable terms will be negligible. So you have y is equal to 0. And for the y-intercept, okay, you have y is equal to 0, or in terms of ordered pairs, you're going to have the origin. All right, now, and looking at what we have in the setup, okay, so just consolidating what we have about the end behavior, the zeros, sign values. Okay, so you've got two distinct zeros. Okay, so you have the origin, which had to be both an x and y intercept. And we have at 5. Okay, now in terms of the end behavior, okay, so you have down to the left, up to the right. So you're going to have downward motion, okay, from down and to the left, okay, from the leftmost 0. And for up to the right, okay, we'll apply this extension away from the rightmost 0. Okay, so you have up and to the right. And again, just for the zeros, okay, at 0 and 5. Again, at 0 the graph is going to touch, and at x equals 5, okay, now you're going to have the graph to cross. Okay, so filling in the empty space. Okay, so you got your end behaviors. Now if I were to go from left to right, okay, so once I get to the origin, okay, now the graph is going to touch. So you got below, touch, you have below once again, and then we have the graph to start to ascend or rise. And once we get to x equals 5, okay, we want to have the graph of f of x to go from below the x-axis to above, where it's going to stay as such for the rest of the graph of this function. Okay, so this will be the behavior. What we have for f of x is equal to x cubed minus 5x squared. And now, in the case of what we have with number 60, okay, and now we're going from f of x to g of x. And for g of x, okay, so you have x to the 5th minus 2x to the fourth. Again, the higher degree term is going to be x to the fifth. And a bit of history to repeat. Okay, so the leading coefficient is going to be 1. So that is positive. Okay, and in terms of the order, okay, we have the n is equal to 5. So you have an odd power. So you have that bit of history from number 59 to repeat. So you got a positive leading coefficient, odd power. So you're going to have the same end behavior, again, down to the left and up to the right. So we have the end behavior. Okay, now looking for the zeros and their multiplicities. Okay, so taking the factored form of g of x. Okay, so with the terms, we're going to have the greatest common factor is going to be at x to the fourth. And again, just stressing the degrees. Okay, so you have g of x. Okay, so you have is equal to x to the fourth. You have times the quantity of x minus 2, no explicitly raised higher power, so this is going to be to the first. And so we have, in the case of the zeros, okay, so from just the x factor, we have x is equal to 0, and from x minus 2, if that is equal to 0, so we have x is equal to 2. And for the multiplicity, okay, so 0 is going to have a multiplicity of 4. X equals 2. It's going to have a multiplicity of 1 since the corresponding factor is raised to the first. And in terms of crossing or touching the x-axis, okay, so again we have an even multiplicity for x is equal to 0. So it's going to touch at the origin. And for x equals 2, okay, again you have an odd multiplicity value. So that's going to cross at x is equal to 2. And for what we have in the case of the y-intercept, okay, so you have y is equal to, and we have g of 0. So you have 0 to the fifth minus 2 times 0 to the fourth. So you have a couple of negligible terms, and so we're going to have the y-intercept to exist only at the origin. So you have for the y-intercept, okay, so you have y is equal to 0, or again specifying the point, okay, we have the origin. And so just looking at what we have in the setup. Okay, so I have the zeros of interest. So I have 0 and 2. Again, for the end behavior, once again we have down to the left. And up to the right. And in terms of the activity, okay, so we have for that which lies in between, namely the zeros. Okay, so the graph is going to touch at the origin and cross at x is equal to 2. Okay, so we have this bit of history to repeat. So we're starting out below. Once we get to the first or the smaller or smallest zero, okay, the graph is going to touch and get back to below the x-axis, and then once we head out to the next and last zero, okay, at 2, okay, so we're transitioning from below to above the x-axis, and the rest of the function of g of x is going to continuously go up and out to the right. And so 59 and 60 can have a lot of similarity in terms of the nature, and as well as the graphs. You got 2 zeros, same manner in terms of touching and crossing. Now, in terms of changing things up a little bit, now we have for number 64, okay, so this time we have this function in the form of h of x. And in the case of what we have for h of x, okay, so we're going to have a trinomial expression of higher order, and we have this set equal to, okay, so we got x to the 4th minus x cubed minus 6x squared. Okay, so we got a trio, and the terms happen to be arranged in descending degree order. It's not always as such. So you look at which term has the highest degree in x. Again, it happens to be the first one, which we have at x to the 4th. Okay, so for x to the 4th, again, we have the leading coefficient is going to be 1. Okay, so this will be positive, and for the degree n, okay, that is going to be 4. Okay, so you have an even powered function. Okay, and so in this case, for the n behavior, okay, because the coefficient is positive, and again, the nature of the function being where the degree is even, the n behavior is going to be up both to the left and to the right. All right, so we have this motion at the extreme ends. Now, for what we have for the in-between activity, okay, this is where the zeros will come in. Okay, so looking at going from this expanded form to the completely factored layout. Okay, so we have the greatest common factor for h of x, okay, that is going to be x squared. We have times quantity, so you have x squared minus x minus 6. Again, this trinomial is factorable, so you have x squared, so you have times the quantity of x plus 2 times that of x minus 3. And just rewriting, okay, and again just stressing the degrees, okay, since the degrees will define the multiplicity. Okay, so you got x to the 2nd, and for x plus 2 and x minus 3, okay, no explicitly raised higher order powers, so those are going to be of degree 1. And so we have for the zeros, from x, okay, we have x is equal to 0. From x plus 2, we have x equal to negative 2. And from x minus 3, okay, we have that x is equal to 3. And from the multiplicities, okay, so you have the degrees that correspond. Okay, so 0 is going to have a multiplicity of 2. Negative 2 is going to have a multiplicity of 1. And so will x equal to 3. And in terms of crossing or touching the x-axis, again, at even valued multiplicities, it'll be at those zeros that the graph touches. And for the odd value multiplicities, okay, at those zeros the graph is going to cross. Again, just looking for the y-intercept. Or intercepts. Okay, so you have for h of 0. So you have 0 to the 4th minus the cube of 0 minus 6 times the square of 0. Okay, so you have zeros throughout. So you have y is equal to 0. And again, we have for the y-intercept, there's only one, and that is going to be the origin. Okay. And just looking at how things are going to play out in terms of the graph itself. Okay, so we have with our zeros. Okay, so we got negative 2. And we got 0. And also we have 3. Okay, so we got our 3 zeros. And again, for the end behavior, we have up to the left and up to the right. So I can just make the projection up to the left from the leftmost 0 up to the right, make that projection from the rightmost 0. So you have up to the left and up to the right, and then we have for the activity among the zeros. Again, at negative 2, again we have the graph to cross. At 0 it is going to touch, and at 3 the graph is going to cross. Okay, so just looking at what we have reading from left to right. Okay, so you have descending. Okay, so you have crossing at x is equal to negative 2. Then it's going to rise and touch at the origin. So it's going to dip, and the graph is going to rise up again. And once we get to x equals 3 and follow through, okay, we're going to have the graph to cross. And this will be the general dynamic of what we have for h of x. And again, I'm not drawing this according to scale. It might look a little bit more or a little bit less like a letter W. Okay. And we've had so far for these cases, we've had the y-intercept to exclusively be the origin. Okay, but now we will have a bit of an exception in the case of number 72. And for this particular function, okay, we have with h of x. And we have another trinomial, and this one's going to have sort of a different nature. Okay, you have negative of x to the 4th plus 10x squared minus 9. Okay, so you got your highest degree term. Again, you have 4th order. So highest degree term. Okay, so you have the negative of x to the 4th. Okay, so for the leading coefficient because of the negative sign. So we have -1. And in the case of the degree, okay, have n is equal to 4. So that's going to be even. Okay, so a polynomial that has a negative leading coefficient, and that is even in degree. Okay, then we have the end behavior to be moving downward to the left as well as to the right. And in the case of the zeros, okay, there's thanks to the negative sign that is at the front, okay, there's going to be a bit of a manipulation to make this factor friendly. Okay, first of all, okay, I think most of us will want to factor out x to the fourth as opposed to negative x to the fourth. So what I can do here is I can just factor out the negative sign, or factor out -1. We're going to have this expression to be the opposite sign of x to the fourth minus 10x squared plus 9. And here we have an expression that is quadratic in form, again, where we have the higher order variable term to be exactly twice the degree of the lower. Okay, so we got for x to the fourth minus 10x squared plus 9. I can factor this trinomial. So for x to the fourth, okay, I can factor this out to x squared and itself. And for factors of 9, that will add up to -10. So you have a -9 and a -1. And both of these factors will be differences of squares. And so we have the negative, again, you have of x plus 3 times x minus 3 you have times the quantity of x plus 1 times that of x minus 1. Okay, and none of these expressions will be raised to any higher degree. So you have x plus 3 to the first, x minus 3 to the first, x plus 1 is to the first, and we have x minus 1 is also raised to the first. Okay. And so we have, with the zeros, we got 4 distinct variable factors, and so we'll have 4 distinct zeros. Okay, so from x plus 3, we have x equal to -3. Now the negative sign, or the -1, that's just a multiple, so it's not an x factor in direct terms. Okay, so from x plus 3, we have x equal to -3. From setting x minus 3 to 0, we have x is equal to 3. With x plus 1, we have x equal to -1. And with x minus 1, okay, we have that x is equal to 1. And for the multiplicities, okay, -3 has a multiplicity of 1. Yes.
So the -1 that's outside of those isn't x equals 0?
That is, okay, the negative that's outside, that's just a coefficient, like -1. In other words, the way to look at this, if you were to envision like the graph of x to the fourth minus 10x squared plus 9, okay, you have it almost like almost like a W shape, but with the negative, it's going to be like flipping that. In other words, it's like the x to the fourth minus 10x squared plus 9 would be almost like a W shape. And what we're about to see with this trinomial, with the negative, you're going to be looking at kind of like the mirroring across the x-axis, where it's going, instead of looking like a W, it's going to look like an M. That negative sign, it's just a multiple. It's just a multiple. It's not an x factor. Only, in other words, I just factored out the negative so I could deal with, factoring out x to the fourth. Okay, so just think, yeah.
Right. So what if it was not a negative and it was just like the number 2? Like if you could factor out the number 2 out of that original equation, you would do nothing with that also?
Okay. What would happen in this one? That would be okay. If I could factor, like if I had like 2x positive 2x to the fourth, I would have different factors in the mix. It might be like 2x squared plus something or minus something, and then x squared plus or minus something, and just get totally different zeros in the mix.
No, I'm not saying like if you could factor out an x, like if it wasn't -1 and what it was outside was just like a number 2.
Gotcha. Okay. Yeah. So let me put it this way: if you had like if all these coefficients were even, and I factored out 2 would not be an x factor. It's just a multiple.
Okay, so there has to be an x there. That's all.
There has to be an x.
Okay. All right. Thanks.
You're welcome. Okay. And so we have okay. So we have with the x factors. Okay. So you have okay. All of these are going to have multiplicity of 1. And it's because all of these have a multiplicity of 1. And since 1 is going to be an odd value, okay, in terms of whether the graph is going to cross or touch the x-axis. Okay, so we have 1, so it's going to cross at x equals -3. We have to cross that x is equal to 3. We have to cross that x equal to -1. And for this last 0, okay, we'll have to cross that x is equal to 1. Okay. And so just taking what we have right now. Okay, so you have these elements. Now for the y-intercept, okay, so y is equal to h of 0. Okay, and there's going to be a bit of a change up. Okay, so we still got the negative. And what's going to be 0 to the fourth? That is going to be negligible. And we have 10 times 0 squared, also negligible. But we have the -9 to follow, not negligible. So you got 0 plus 0 minus 9. So this will go to -9. So you're going to have a y-intercept away from the origin. So for the y-intercept, we have a y is equal to -9, or in ordered pair terms, okay, this is going to be at 0, -9. Okay, and taking what we have for the graph itself, okay, and we have just mentioning the intercepts. Okay. Okay. So you got x equal to -3. So you have x equal to -1. We have x equal to 1. And we have the x is equal to 3. And for what we have on the y-axis, okay, we have 0, -9. Okay. And in terms of what we have at the extreme ends, okay, so you have the end behavior, you have down to the left and down to the right. So projecting from the leftmost and rightmost zeros. And behaviors have down to the left and down to the right. and for what we have in between. Okay, so you have throughout, we want to have crossing the x-axis. Okay, and looking at setting things in motion. Okay, so you got down to the left, down to the right, and for the stuff in between, moving from left to right. Okay, so at -3, the graph is going to cross from below to above the x-axis. And then the graph is going to descend once we get to x equals -1. Okay, we have crossing from above to below, and it's going to dip and cross the y-axis at y is equal to -9. Somewhere it's going to rise up, and it's going to cross at x is equal to 1. And then somewhere it's going to peak out, have a relative maximum, and then start to dip. And for the rest of the activity, it's going to arrive at x equals 3 and cross over, and the rest of the graph of h of x is going to be below the x-axis. Alright, okay, so you have odd multiplicities exclusively, so the only activity on the x-axis was where the graph is crossing. Alright, and now looking at polynomial functions, okay, and taking a bit of a break from the graphing, and just going back to forming polynomials from zeros and their multiplicities. Okay, and one of these, okay, will be just kind of well, not so much a repeat, but just kind of a reminder of stating that, okay, a multiplicity of a zero is going to be the degree to which the factor corresponding to that zero is going to be raised. Okay, and okay, and looking at continuing, okay, this particular part. And we'll just look at determining an expanded form. Okay. Notice I said determine an expanded form, not the expanded form. Okay. You might have, it could be, some of these can be expressed in different ways. And let's say that we have given, okay, say we have zeros, and we'll say we have x is equal to 0. Where the multiplicity is equal to 3. And also we have x is equal to -4. Where the multiplicity is equal to 2. And we'll have the degree of the polynomial to be at 5. Okay, so for this, okay, and a lot of cases, okay, the degree of the polynomial will be the sum of these multiplicities. Okay, so from x is equal to 0, okay, we say that corresponding factor, okay, we'll have x. From x is equal to -4, we can say that this originates from x plus 4. Okay, just those factors, but now with the multiplicities included as higher numbers. Okay, so 0 has a multiplicity of 3, so we have not just x, but x to the third. And with negative 4 consisting of a multiplicity value of 2, we have not just x plus 4, but x plus 4 raised to the second. And in the case of what we have for f of x, okay, so we have x to the third times the square of x plus 4. And if we look at multiplying out, and there are different ways you can go about this. You could square out x plus 4 in advance, like x cubed over x squared plus 8x plus 16. That's one viable choice. We should also write the square of x plus 4 as x plus 4 times itself. And I can just group together, or I should say multiply x cubed in the first x plus 4. I can go through that route as well. And if I were to, okay, so I have x cubed over the quantity of x plus 4. See, this will be x to the fourth plus 4x cubed. And have this x plus 4 waiting to be multiplied. And taking the FOIL method, okay, so you have x to the fourth times x. Okay, so this will be x to the fifth. And we have the outside product is at 4x to the fourth. Inside product 4x cubed times x. Okay, so that's going to be 4x to the fourth. And 4x cubed times 4. Okay, so this will be 16x cubed. So you have for f of x. Okay, so this will be x to the fifth plus 8x to the fourth plus 16x cubed. Okay, so this is one expanded form of a polynomial that have those zeros and corresponding multiplicities. And also where we have the degree of the function is at 5. Okay, now let's say, so far we have dealt with zeros that are of integer values. But let's say if we have something that could be non-integers. I know to let these zeros be a multiplicity 1. And we'll say we have in one case we can have x is equal to negative 2/3. We have a multiplicity of 1. And we can also have x is equal to 4/5. Which has a multiplicity of 1. And for the degree of the polynomial, we have this to be a second degree. Alright, and now ways you can go about this. So you have x equals negative 2/3. And you could take this as possibly originating from x plus 2/3. And you can alter this. And for x equals 4/5, we can say that this is going to originate from setting x minus 4/5 to 0. And you can set up a factored form here we have the quantity of x plus 2/3 is multiplied by the quantity of x minus 4/5. And you can keep the fractions in the factored form set up. Okay, but I'll just mention this. I'm going to follow through in this fashion. You can eliminate the fractions by raising the coefficients. And what I mean by this, okay, say you have, if I want to alter what I have here, okay, so I have x plus 2/3. Okay, and what can take care of thirds? You know, we can say we have multiplying by 3. And for x minus 4/5, okay, so the fraction is in fifths. So how can I take care of fifths or clear out fifths? Well, I can multiply by 5. So I can rewrite these two binomial expressions. Okay, x plus 2/3 if I multiply by 3. I'm going to have 3x plus 2. And for 5 over x minus 4/5, okay, so that's going to be 5x minus 4. Now I'll just mention, okay, so again, it's not going to do anything in terms of what we have for the zeros. If I were to set 3x plus 2 equal to 0, 3x is equal to negative 2, x equals negative 2/3. If 5x minus 4 is 0, 5x equals 4. Division by 5 leads to x is equal to 4/5. So I just raise the coefficients here, and if I FOIL out, okay, so I have 3x times 5x, so this will be 15x squared. Then we've got minus 12x. Then we've got plus 10x for the inside product. And last product, okay, we have it negative 8. And so, an expanded form of what we have here. Okay, so we have f of x is equal to 15x squared, and for the variable terms in the middle, negative 12x plus 10x, we have minus 2x, and the constant at the end, okay, we have at minus 8. Okay, so this is one form. And now I'm just going to mention, if I had worked with what I had originally, okay, by raising the coefficients, I multiplied the factor form, not just by 3 or only by 5, but I multiplied by 3 times 5. So I raised this by a factor of 15. And had I kept this original setup, another expanded form would have been where the result would be x squared. In other words, 1/15 of this result, where I would have x squared minus 2/15 of x minus 8/15. And that would have been your result had you kept the fractions from the start. Right. So you will have some of your polynomials to consist of zeros that are integers, but in this particular case, you will have possibly the inclusion of zeros that are non-integers. And now, again, in terms of operations among polynomials, we've had all kinds of items, and we've had factoring, FOILing out, looking at zeros, multiplicity. So we've looked at everything like multiplication, division, as well as looking at exponents. And now in the case of interacting polynomials, and we have for this portion, we have what is going to be regarded as polynomial division. And there are two modes we're going to be looking into. Okay, one is going to be log division, and the other is going to be synthetic division. Let's say if we have, just as an example, okay, if we have x squared plus 4x plus 9 is divided by x minus 2. by long division. Okay. Where you're going to set this up, so you have x minus 2 then we have taking into x squared plus 4x plus 9. Okay, so we have, first of all, okay, taking what's going to be the divisor into this trinomial. Okay, so we're going to look at the first term. So look at x and x squared. Okay, so if I were to take x into x squared, or x squared divided by x, that's going to leave us with x. And what I'm going to do here is kind of do a little bit of working on the side here. So you have x times the quantity of x minus 2. So you have x squared minus 2x. Well, what am I going to do with x squared minus 2x? I'm going to have x squared and negative 2x placed beneath the like terms from this trinomial. So I have x squared minus 2x. And what am I going to do to these? Well, I'm going to subtract. Okay, so with long division, you're going to be looking at row by row subtracting. And looking at subtracting the corresponding parts. Now, whatever comes from the dividend, or the trinomial in this case, I want the first term to be eliminated, and anything that evolves from this to also go out. So we're going to have x squared minus x squared completely cancels. Now we've got 4x minus negative 2x. It's going to be 4x plus 2x, which will make 6x. Then we have plus 9. Okay, now I got first term before was x squared, now it is 6x, and I can take x into 6x 6 times. And if I look at distributing, okay, so I have 6 over the quantity of x minus 2. So this will be 6x minus 12, and I'm going to place 6x minus 12 underneath. And we have subtracting, so we have 6x minus 6x goes out. 9 minus negative 12, okay, that's going to be 9 plus 12, which is going to be 21. And now I cannot take x directly into 21. And for this result, okay, you're going to have the remainder at 21. And now for the x plus 6. X plus 6 is going to be what is regarded as the quotient. Now, say if we have this same expression, I'm going to show you another way. And we have bisynthetic division. Okay, so again, I'm taking x minus 2 into x squared plus 4x plus 9. Okay, and what I'm going to do here, setup is going to be quite different. I'm going to do, instead of taking all of x minus 2, I'm going to take the 0 of x minus 2, which is going to be 2. So I'm going to have kind of a column formation. So I got 2, this will be the 0. And for the coefficients of x squared plus 4x plus 9, we'll have 1, 4, and 9. Now where I had row by row subtracting with the long division, synthetic division is going to call for column by column addition. So what I'm going to do here, okay, is that whatever the leading coefficient from the dividend, in this case 1, whatever that is going to be brought down. So 1 is brought down. And then we'll have the 0, 2. Okay, so I got to bring down 1. 2 times 1 is 2. 2 is going to be brought to the next column. And then we got 4 plus 2 is 6. For that next total, I'm going to multiply by, again, the 0, which is 2. 2 times 6 is 12. And then we have 9 plus 12 is going to make 21. And guess what? For this last column total, again, you're going to have the remainder at 21. And guess what? For the 1 and the 6, the 1 and the 6 that will precede that, okay, that's going to make reference to the quotient. Again, 149 reference x squared plus 4x plus 9. And at the bottom, the 1 and the 6 are in reference to 1x plus 6. And you've got the same remainder